Although our knowledge about extraterrestrial exospheres is very limited, we know more about Venus and Mars exospheres than we know about Earth. But why is this the case? Because we lack accurate in situ chemical composition measurements performed with mass spectrometers. Mass spectrometers provide data of the chemical composition of a celestial object. Former instruments include the GPMS on board the Galileo probe, the INMS on board Cassini, the GCMS on board the Cassini-Huygens, the RTOF on board Rosina Rosetta, and the NMS on board Lade. The aim of all these instruments is, of course, to perform highly quantitative in situ measurements. However, different techniques exist to realize this goal. Currently used techniques for mass analyzer include magnetic sector instruments, quadrupoles, and time-of-flight instruments. Magnetic sector instruments and quadrupoles have, however, major drawbacks when compared to time-of-flight instruments. These instruments scan over the whole mass range, meaning that they are first only able to see what they want to see, and second, the acquisition of a full mass spectrum is very time-consuming. This is especially an issue when the time needed to record a mass spectrum directly translates into spatial resolution, for example, when orbiting a planet or when descending as a descent probe. Thus, valuable criteria to judge on the performance of mass spectrometers not only include the dynamic range and the mass range, but also how long it takes to achieve these specs. In contrast, the time-of-flight technique provides a possibility to overcome this issue, as a spectrum is recorded at once, and prolonging the duration of measurement only increases the signal-to-noise ratio. The instruments shown on the slide represent instruments from former or upcoming missions. It is unquestioned that those instruments boosted or will boost our knowledge about the origin and evolution of solar system objects. However, from today's perspective, the technology is outdated. In fact, from today's mission perspective point of view, those instruments are a nightmare. For example, former mass spectrometers consumed power of more than 30 watts. This, of course, has decreased for upcoming flight instruments such as the NIMPEP-JUICE and the NGMS on board Luna Resource or Luna 27. Another issue is the mass of the instruments. For example, the INMS weighed 10 kilograms, including 1.4 kilograms of shielding. Newer instruments, such as the NIM and the NGMS, consume about 3.2 kilograms, excluding shielding. This transition reflects the trend of miniaturization in mass spectrometry as well. This trend can be simply illustrated by measuring the length of the instrument, which is approximately equal to the length of the drift tube. A 100 centimeter class of instrument is represented by the RTOF on Rosina Rosetta. Smaller instruments include the newer NIMPEP-JUICE or the NGMS on board Luna Resource. Both of them represent the 30 centimeter class of instruments. As the mass resolution decreases with the decreased length of the drift tube, maintaining a reasonable mass resolution for small instruments remains challenging. To provide some numbers, the RTOF had a mass resolution of close to 5000 full width F maximum, and the NGMS still has a mass resolution of about 1200 for higher masses. In addition to the resource consumption, those instruments were highly customized, resulting in high development costs and a development time ranging from 5 to more than 10 years. Thus, we developed the time-of-flight mass spectrometer, which is a representative of the 10 centimeter class of instruments, and modular at once. Such an instrument provides three main use cases, which I discuss now before discussing details of the instrument. First, such an instrument can be applied to analyze the terrestrial exosphere. The terrestrial exosphere represents the uppermost layer of Earth's atmosphere. It is mainly characterized by the number of species present, the chemical composition of those species, and the temperature of them. By now, we have only little knowledge about Earth's exosphere. In fact, the latest valuable scientific measurements date back to 1983. The left panel shows the number density versus altitude. For higher altitudes, the number densities are represented by straight lines, These straight lines represent the exponentially decreasing number density profile, which originates from models of the exosphere by assuming hydrostatic equilibrium. The negative inverse of this exponent of this function represents the atmospheric scale height of species, which are not well constrained given the lack of accurate in situ measurements. But knowing the scale heights is a crucial information to determine atmospheric escape now and over time. Atmospheric escape is thought to be one of the reasons why Earth is habitable and Venus and Mars are not today. Knowing today's scale heights would already be wonderful, but from a scientific point of view, the drivers are also of interest. Apparently, the scale heights are not constant over time, as shown in the central panel. The central panel shows temperature over altitude. Temperature and the scale heights relate via the hydrostatic equilibrium. Now, apparently, there is a big difference between the solar minimum and the solar maximum temperatures in the exosphere. Also, we have a long trend shown in the right panel. There, the number density is shown over a period of 40 years. Here, we see that the order of magnitude in the number density present at the 400-kilometer orbit differs for more than one order of magnitude. Potential drivers could include solar parameters such as ultraviolet radiation, solar wind, and solar cycle, as well as others such as the moon or even an outgassing of the Earth was proposed. Other open questions are variations at the day-night side terminator and night-side transport of species. Species of interest include major species such as the CNOH elements, the neutrals, ions, minor species, and traces of elements. To answer all these questions, we need to perform highly accurate in situ chemical composition measurements with a high temporal and spatial resolution. Second, exospheres of other planets can be analyzed. As already indicated, Venus, Earth, and Mars differ a lot. This is also true for the exosphere, not only for the temperature, but also for the atmospheric escape rates. This difference in atmospheric escape rates could have resulted in a habitable planet such as Earth. Also, we learn about the evolution of those planets by measuring the noble gases at the exosphere, as the noble gases are chemically inert. Measuring noble gases on Venus with today's mass spectrometer technology is possible, for example, on Venus, as Gruchola showed in her paper 2019. Venus is a planet where flybys frequently happen, especially when visiting the outer solar system. During such a flyby, the primary payload would deploy the secondary payload, which consists of our mass spectrometer, a service unit, and an additional payload. This secondary payload would then communicate with the primary payload, which operates as a relay. The secondary payload would then descend through the exosphere until it reaches the deep atmosphere where the pressure is high enough so that the probe stops operating. A key requirement for the mass spectrometer here is that it is able to analyze heavier isotopes of noble gases such as krypton and xenon. This is possible when achieving mass resolutions of over 200 full width half maximum when including margin. Additionally, an isotope ratio with an accuracy of about 1 to 10% is demanded. Third, the instrument can measure ambient gas. To measure certain species in the atmosphere, one has to reach low altitudes, as species may freeze out in clouds. Measuring at low altitudes is, however, only possible when a vacuum system is provided by the spacecraft. In contrast to the previous two use cases, measuring the deep atmosphere therefore asks for analyzing thermal or ambient gas. By design, our instrument has an energy-tolerant ion source, meaning that it is able to analyze both the ambient gas and gas at orbital velocities. Thanks to this design feature and a small footprint of the instrument, it is able to be packed in a vacuum system and sent to, for example, Neptune or Uranus as a primary or secondary payload. Other applications are in the lab, where one wants to monitor plasma processes or in situ measurements, such as, for example, the behavior of irradiated ice. For all the said reasons, we developed the CubeSatTOF instrument. CubeSatTOF is a compact time-of-flight instrument which fits into 1 unit. Its ion optics has a footprint of 10 by 10 by 2.6 centimeters cubed. The figure I show on the right represents a flight-like ion optical system with a prototype detector, which is why it's increased in size. The left panel shows a cartoon of concept of operation of the CubeSatTOF instrument, or the use case in the Terrestrial Exosphere in Leo. The CubeSatTOF instrument is aboard a 3-unit spacecraft consisting of the mass spectrometer itself, an additional payload, and a service unit. This spacecraft will orbit Earth in an elliptical orbit in Leo. Such an orbit allows for measurements at various altitudes. Thus, we can analyze the upper thermosphere and the exosphere as well. The instrument consists of 2 major units, the sensor and the electronics. The sensor can be grouped into the functional elements, which are the ion source, the reflectron, the detector, and the drift tube. 3 operation modes are possible. In the first mode, ions enter the ion source at orbital velocities. In the second mode, they do this as well, but they get ionized with a filament, as shown in figure A. In the third mode, ambient gas is analyzed. Therefore, it analyzes the neutral species which are already present in the ion source. Once ionized, species travel through the drift tube, where they separate in mass per charge ratio to the ion mirror, the reflectron, where they are reflected towards another drift tube and then registered at the detector. While the ion optics remains roughly the same for a vast majority of missions, the electronics can be adapted so that it fits the need of the mission. We designed the instrument in such a way that it's easily possible to replace the COTS part with high-yield parts. This considerably decreases the engineering effort needed to be selected for a mission where radiation tolerance is crucial. Also, and often underestimated, the software remains mostly the same, as only low-level drivers need to be adjusted, if at all. We tested the ion optical system I showed before in the laboratory with thermal gas. The left panel shows 3 data series. 2 of them were derived from SIMION, and 1 of them from the laboratory measurements on raw data. When measuring thermal velocities, the mass resolution stays roughly constant over the mass range. When measuring orbital velocities of species, then we have a selectable maximum of the mass resolution in the instrument. The maximum is not shown within the mass range I show in this panel. The right panel shows the background-corrected mass spectrum in the mass range between 0 and 140. The mass resolution of 240 at xenon is calculated from raw data. This measurement of the ambient gas with calibration gas demonstrates that we are able to resolve xenon and therefore analyze its isotopes. Also, note the dynamic range indicated by the y-axis, despite that this NIM prototype detector has a too small active detection area. We summarize the requirements of likely upcoming missions and build an energy-tolerant ion optical system in accordance to these requirements. Our instrument is able to perform chemical composition measurements with a mass resolution of over 240 full width of maximum. Enabled by its high mass resolution, our instrument performs chemical composition measurements, including a highly accurate analysis of isotopes of CNOH elements, including the valuable D/H ratio, and noble gases, including krypton and xenon. The expected sensitivity provides the opportunity of an application in LEO, in the likely upcoming CHESS mission, which aims to create an inventory of the chemical species present at the exosphere starting from the end of 2022 or in early 2023. In addition, the mass resolution we demonstrated here equips the instrument with a unique feature so that the instrument can be considered as a descent probe deployed from a primary spacecraft during a flyby of, for example, Venus. In conclusion, we developed a 1-unit time-of-flight mass spectrometer which represents the 10 cm class of instruments. Despite the small footprint, it is high performance and able to perform chemical composition measurements, including isotope analysis of heavier noble gases such as krypton and xenon. The CubeSatTOF instrument enables us to investigate the terrestrial and extraterrestrial exospheres to improve our understanding about the origin and evolution of celestial objects, and therefore answer questions related to the differences concerning habitability between Earth, Venus, and Mars.